Now in this session, we will see the different types of reactions like zero order, first order, second order type of reactions. So just try to understand what is the meaning of these different types of reactions. So first one is a zero order reaction or zero order process. Now as per as the name is considered, or as the name suggests, the rate of reaction is not dependent on concentration of any reacting species or which is taking part in the reaction. So we can say that in case of zero order reactions, the rate of reaction is independent on concentration. It does not depend on the concentration. As it is independent on the concentration, the rate of zero order reaction is independent on concentration. The rate of the reaction cannot be increased further by increasing the concentration of reactants. So as the rate is independent on the concentration, if we increase the concentration of the reactants, there will be no effect on the rate of reaction, because the rate of reaction, as we have defined, is independent on the concentration. So whatever will be the concentration, or the whatever may be the concentration, the rate of reaction will be constant. The concentration will not affect the rate of reaction. So these reactions are also known as, or this process are known as a constant rate processes or the constant rate reaction, because the increase in concentration does not affect the rate of reaction. That expression for the zero order reaction can be given by minus dc by dt is equal to k0. So k0 is a zero order reaction rate constant, and as dc by dt is a rate of reaction, it does not dependent on the concentration of any reacting species. The example of zero order reaction is the loss in color of the multisulfur product. The multisulfur drugs, they generally have the color, and it was observed that in case of the multisulfur product, the color fading occurs. They are colored compounds. There is a fading of color occurs during storage, but it was found that the color, the intensity decrease or decrease in intensity of the color is not dependent on the original color or original intensity of the color. As the time proceeds, there is a fading of the color of the multisulfur product, but that fading was observed as a constant process. It doesn't depend on the intensity of the color. So that's why that is an example of the zero order reaction, which does not depend on the concentration. In this case, the parameter is color. The reaction is for now. Now see this graph. In this graph, you can see when the concentration is plotted against the time, you will get a straight line that indicate the process is constant rate process. It does not depend on the initial concentration. The rate of reaction will be same throughout the reaction, throughout the period for which the reaction proceeds. Now we'll see the next concept, that is the pseudo zero order type of the reaction or the apparent zero order type of the reaction. As we have seen earlier also, pseudo means the reaction is actually a different order, but it behave like a different order reaction. So obviously the pseudo zero order reaction, actually it is a first order type of the reaction, but it behave like a zero order. So that's why it is known as a pseudo zero order type of the reaction. Now example is the suspension. The classical example of the pseudo zero order reaction is a suspension. Now in the suspension, we know that solid particles are also present, and the solid drug particles are also present, and the some drug is present in the solution form also. But these solid particles which are present in the suspension, they act like a reservoir. As the concentration of the drug in the solution decompose or decrease, the solid particles release some amount of the drug, and finally the concentration of drug in the solution remains constant. That's why the reaction behave like a zero order, because in zero order we know that there is no effect of concentration on the rate of reaction. So in this case also, as the solid particles are acting like a reservoir, as soon as the concentration of drug in the solution decompose, some drug is released from the solid particles. That's why the concentration of drug in the solution remains constant. So actually this reaction is a first order. If you remove the reservoir, you will find that as the drug concentration in the solution will decrease, concentration of drug in the solution decrease, the rate of reaction will also decrease because the reservoir is absent. But as in case of the suspension, the solid particles act like a reservoir. So as soon as the drug concentration falls, solid particles release some amount of the drug. This process continues so that the concentration of the drug in the solution remains constant, and that's why the rate of reaction is also constant, as it is independent on the concentration. But at a certain stage, if the solid particles in the suspension are not present, then you will find that the reaction will behave like a first order because there is no reservoir. In that case, as the drug concentration in the solution will decrease, the rate of reaction will also decrease. So it is dependent on concentration now. So such type of the reaction which are actually first order but behave like a zero order, that is known as a pseudo zero order type of the reaction. Next concept is a first order reaction. Now you know the zero order, it is independent on the concentration, that is the rate of reaction. In case of the first order, the rate of reaction depends on concentration of one of the reactant or one of the reacting species. So first means one, so obviously the rate of reaction depends on the concentration of one of the reacting species. So as the concentration of the reacting species will change or the reactant will change, there is a change in concentration, there is a change in rate of reaction also. So it depends on the concentration. Example is the hydrogen peroxide decomposition, which is catalyzed by the 0.02 molar potassium iodide. So the rate of reaction is proportional to the hydrogen peroxide catalyzed. As the concentration will decrease, the rate of reaction will also decrease. The reaction is shown. You can see the reaction. And the rate of reaction is given by minus dc by dt is equal to K into C. So C is introduced here because rate of reaction depends on the concentration, and K is a reaction rate constant for the first order. Now these are the various forms of the equation for the first order, but the final equation you must remember, that is a K is equal to 2.303 upon T into log of C0 by C. So that is the integrated form of equation for the first order, and below that the exponential equation is also given, that is C is equal to C0 e to the power minus KT. Now these are the graphs for the first order reaction. You can see that concentration versus time graph. In case of the first order, there is a decrease in the rate of reaction. As the time will proceed, the concentration will decrease and the rate of reaction also decreases. That minus dc by dt will decrease. Minus because there is a decrease in rate of reaction with time, as it is dependent on the concentration. Initially you can see there is a high concentration, so rate of reaction will be higher. As the concentration decrease, the rate of reaction also decreases. And if we convert that this plot, if you plot this graph on the log scale, that is the log concentration versus time, so in that case you will observe the straight line. So in case of zero order, concentration versus time gives the straight line, whereas in case of the first order, log concentration versus time gives the straight line. So in that way also we can differentiate between the zero order and the first order. Now next one is the second order type of the reaction. Obviously the rate of reaction depends on concentration of two reactants, each raised to power 1. A plus B giving product, that is the example, means the rate of reaction depends on A as well as B. So these are now we'll see the rate of reaction given by minus dA by dt or minus that is dB by dt is equal to K A into B, means it depends on concentration of both the reacting species. Now in this case we can have the two equations. See, when the concentration of two components reacting in the second order reaction, that is A and B are equal or A and B are not equal. So in that case we can have the two different equation, like The equations are shown in this case for when the concentrations are equal and concentrations are not equal. Equation for the second order. These are the integrated form of the equation for the second order. Now next concept is a half-life that everyone might be knowing. The period of time required for a drug to decompose to one half of the original concentration. Means if the original concentration is 100, then time required to decrease the concentration to 50%, that time is known as a half-life. Now half-life equation is different for the different order. Like zero order, we can have the equation. This equation shown here is the first order equation, that is T half is equal to 0.693 upon k is for the first order. Similarly, we can have for the second order or the zero order also. So that is the meaning of half-life. Now units of the basic rate constant, like zero order, first order, second order, units are given. It just depend on the equations. Like rate of reaction does not depend on the concentration, so we can have the minus dA by dt. So dA is a concentration and dt is a time. The concentration in moles per liter and dt is a time, that is in second. So we can have moles per liter per second. Similarly, we can have the units for the first order and the second order type of the reaction. You can just see, we'll come to know. Now we'll see the methods for determination of order of reaction. Now everyone knows what is the meaning of order of reaction. The sum of the exponents or the sum of concentration terms on which the rate of reaction depends. Means if the rate of reaction depends on only one concentration of one reactant, the order is 1. If the rate of reaction depends on concentration of two reactant, then order is 2. Likewise, so you know the meaning of order of reaction. We'll see the methods to determine the order of reaction. The first method is a substitution method, is a simple method. Now in this case, just in case of the substitution method, just conduct the kinetic experiment. Means take some parameter like temperature or concentration and see what is the effect of temperature and concentration. What is the effect of temperature, what is the effect of time, or how the concentration changes with time. So let us see, conduct the kinetic experiment and collect the data on the time course of changes in the concentration of the reactant. So what is the effect of time on the concentration? As the reaction proceeds, what happens to the concentration? So just note down that and substitute the data in the integral equation of zero, first and second order reactions to get the k values. So just conduct the experiment like for decomposition of drug at different time intervals. So what happens to the drug concentration with respect to time? So now calculate the k value for each time. For example, you are taken sample for so you are taken sample 4 times, like 1 hour, 2 hour, 3 hour and 4 hour. So determine the k value for each time and just put the values in the zero order, first order and second order reactions to get the k values. Once you have determined the k value, that is a reaction rate constant, just find out or just observe in which case, whether in case of zero order or first order or second order, you are getting the k values constant. The values of the k should be constant. The order in which you are getting the k value constant, the reaction is considered to be of that order. So simply conduct the experiment, collect the data, that is a time course of changes, means how there is a change in concentration with respect to time. Calculate the k value for different time intervals by using the integrated form of the equation and just find out in which case the k value remains constant in case of zero, first or second order. So that it will give the order of reaction in which the k value remains constant. Next one is a graphic method. Now in this case also conduct the experiment, collect the data, that is how time affect the concentration of the reactant, and after collecting the data, plot the graph between the concentration and time. Now the graph which gives the best fit or the better fit for a straight line, the graph in which you will get the straight line, ideal line or the straight line, the reaction is considered to be of that order. Now once you have conducted the kinetic experiment and collected the data how changes, there is a change in concentration with respect to time, then plot the graphs, various graphs. If a straight line results when the concentration is plotted against time, if you plot the graph between concentration and time and you are getting a perfect straight line, the reaction is zero order. If you plot the graph between log concentration and time and you are getting a straight line, the reaction is first order. If you plot the graph of 1 upon a minus x versus time, reciprocal of concentration versus time, that gives the second order reaction. And if you plot the graph of 1 upon a minus x square against t, that is 1 upon c square against t, produces straight line, then the reaction is considered of the third order. So just plot the graphs and just find out in which case you are getting a straight line. So reaction is considered to be of that order. So that is a simple method, a graphic method. And third one is the half-life method. So in case of the half-life method, there are some certain relationship. In case of zero order, the half-life is proportional to the initial concentration, which is given by the A, or we can denote it by the C also. The half-life of the first order is independent on the initial concentration. So these are certain general relationship between the half-life and the concentration. And T half for second order, in which A is equal to B, is proportional to 1 upon A, that is inversely proportional to the concentration. And finally, in case of third order also, the T half is proportional to 1 upon A square. So these are certain generalizations, but we can have the common relationship between these results, that is the half-life of a reaction in which the concentration of reactant are identical can be given by T half is proportional to 1 upon A raised to n minus 1. Now this is our common observation. So T half, we can write the common equation for all these orders like zero order, first order, second order, third order. So T half is proportional to 1 upon A raised to n minus 1, where n, that is a small n, is the order of reaction that we have to determine. Now if two reactions are run at different initial concentrations, that is A1 and A2, the respective half-lives, that is T half 1 and T half 2 for the two reactions, can be given by this equation. So we can rearrange the equation. Now convert that equation into the log form, we will get the final equation, that is and after rearrangement, n is equal to log of T half 1 by T half 2 upon log of A2 by A1 plus 1. Now by this equation, that n is the order of reactions, we can easily find out the order of the reaction. Now simply we can take the example, for example, if the T half 1 and T half 2, as in the case of the first order reaction, if these are same, for example T half 1 value is also 2 and T half 2 value is also 2. So 2 by 2 is equal to 1 and log 1 is equal to 0. So 0 upon log of A2 by A1 means 0. So 0 plus 1 will be equal to 1. So order of reaction, that n is equal to 1. So in this way we can calculate the order of the reaction by the half-life method. So overall there are three methods: substitution method, graphic method, and the half-life method to determine the order of the reaction. So these are the simple methods to determine the order of reaction.